Okay, welcome. This is the first of two 30-minute sessions that will tell you all you need to know to be ready to teach our new Pearson Edexcel GCSE Computer Science in September. We've put together a toolkit of essential documents, and you may find it helpful to download it before continuing. So in this session, we'll be focusing on the structure and content of the 2020 specification. In the next session, we'll turn our attention to course planning, strategies for developing students' problem-solving and programming skills, and introduce you to some of the support materials available from Pearson and others. Changes to the assessment of GCSE Computer Science have come about in response to evidence of widespread rule breaches in which non-examined assessment, NEA, programming tasks were posted online and solutions openly discussed. In response, having consulted with stakeholders, Ofqual announced in January 2019 that students taking GCSE Computer Science would no longer complete an assessed programming project. Instead, from the summer of 2022 onward, all assessment, including the assessment of programming, would be by examination only. Ofqual didn't specify what form this assessment should take, other than that it must be an exam set and marked by the awarding organisation. Awarding organisations were encouraged to be innovative in their approach to examining programming skills. Following Ofqual's announcement, we consulted widely with teachers, examiners and subject experts to decide how best to respond. Teachers told us in no uncertain terms that their students really enjoyed the practical aspects of the course and would be disincentivised to learn to program if their ability to write code no longer contributed to their grade. With this in mind, we decided to make computational thinking and programming the focal point of our qualification and to assess students' practical capability via an on-screen exam. Our many years of experience of designing effective on-screen exams in other computing qualifications, including CIDA and IGCSE Computer Science, proved very useful. It has helped us devise an assessment that truly enables students to show what they can do and is accessible to students of all abilities. Our new GCSE has a good balance of theory and practical work, providing students with a well-rounded experience of computer science. The practical exam has a weighting of 50%, which will give students a real incentive to learn to program. By stripping out some of the theory content and concentrating on the basics, students will get a deeper understanding of key concepts, which will stand them in good stead should they decide to continue studying the subject post-16. We think this course will whet their appetite to pursue the subject further and will give them the knowledge and skills that they need to progress smoothly onto an A-level or a BTEC Level 3 qualification in computing. Our 2020 specification represents incremental improvement rather than radical change. We've organised and streamlined the subject content to give you more time to focus on core principles and concepts, and to free up sufficient curriculum time for students to develop their practical programming and computational thinking skills. Some topics, such as databases and sign and magnitude representation of numbers, have been removed altogether. Some, such as compression and network topologies, have been pruned back. We know that students are keen to explore issues relating to cybersecurity, so we've added a new section covering types of malware, hacking, and social engineering techniques. You can find out more information about the changes to the subject content in the Getting Started guide. There's a copy in your download pack, and it will be referred to several times during this session, so you might find it helpful to have it to hand. Some items in our 2018 and 2019 exam papers did not perform as we had intended. With this in mind, we've worked hard to improve the assessment experience for students by clarifying what content is assessed in each paper, limiting the number of command words used, and explaining what sort of response each requires. We've reduced the number of approved high-level programming languages to just one, enabling us to do away with the need to require students to learn a semi-formal pseudocode. We'll look at this in more detail later in this session. The qualifications, aims and objectives are to build on students' prior knowledge, understanding and skills established through the computer science strand of the programme of study at Key Stage 3, to develop and broaden their understanding of the fundamental principles and concepts of computer science, abstraction, decomposition, logic, algorithms and data representation, to foster their computational thinking skills, enabling them to analyse problems and design, write and debug programs to solve them, to enhance their knowledge of the components of digital systems and how they communicate with one another and with other systems, and raise awareness of some of the issues and impacts associated with the use of digital technology. And finally, to develop students' ability to apply mathematical skills relevant to computer science. Our new qualification has the same balance of theory and practical application as our legacy specification, and the same simple structure. The subject content, what students need to know, understand and be able to do, is divided into 6 topics, shown here on the left. We'll be summarising what is included in each topic later in the session. There are 2 equally weighted papers, seen here on the right, each marked out of 75, and contributing 50% to the final qualification grade. Paper 1 is a conventional 1.5-hour written exam which assesses content from topics 1 to 5. Topic 6, problem solving and programming, is assessed in paper 2, which consists of a number of task-based questions to which students respond using a computer to edit and write code. Having 2 very different but equally weighted papers gives every student a chance to play to their strength, regardless of whether they perform better on a written paper or a practical assessment. We'll talk about the 2 papers later in this session. You'll find it helpful to refer to the specification and the Getting Started guide, both in your download pack, for this next section. Extracts of both documents are shown side by side on this slide, so as to illustrate how the 2 are intended to work together, with the Getting Started guide providing additional information about the subject content and flagging up questions in the sample papers. That shows how the content may be assessed. The subject content on pages 7 to 14 of the specification details exactly what students have to learn. It is important that you understand the conventions we've used. The screenshot on the left is from page 9 of the specification and shows part of topic 2, data. Each of the 6 topics is divided into a number of sections, and each section consists of a set of numbered statements. Section 2.1 is binary. There are 6 numbered statements specifying what students need to understand and/or be able to do. As you can see, statement 2.1.4 starts with be able to, denoting something practical that students will have to be able to do. In this case, add together 2 binary numbers and shift the bits in the binary number left and right. Statement 2.1.5 starts with understand. It specifies it's a piece of theory that students are expected to learn. Statement 2.1.6 has both an understand and a be able to. In this case, students need to learn why hexadecimal notation is used and how to convert between binary and hex. Bracketed lists, like the one in statement 2.1.3, indicate the breadth of coverage required. Statement 2.1.2 illustrates the value of using the subject content and the Getting Started guide together. In this case, the Getting Started guide draws attention to a pertinent exam question that assesses this content and makes it clear that students do not need to know about sign magnitude representation of signed integers or how real numbers are represented in binary. We're now going to look briefly at each of the 6 topics in turn. Topic 1 is computational thinking. You'll find it on pages 7 and 8 of the specification. This topic provides the underpinning theory for topic 6, problem solving with programming. It is divided into 3 sections. The first section deals with decomposition and abstraction. Students need to understand that decomposition involves breaking a complex problem down into a number of smaller, easier to understand subproblems, and that abstraction is the process of removing any unnecessary detail. Here, the focus is on understanding the benefits of using these techniques. Students will learn how and when to use them as they develop their programming skills. Section 2 deals with algorithms. Students must be proficient at following and writing algorithms expressed as flowcharts, pseudocode, by which we mean informal written descriptions, and program code. There is no longer any need for students to learn a semi-formal pseudocode language, a change that has been almost universally welcomed. Students must understand the need for and purpose of variables, constants, data structures, and operators, the what and why. How they are used is covered in topic 6. They must be able to use a trace table to simulate the execution of an algorithm and determine the correct output for a given set of data. As well as being able to identify and correct logic errors in algorithms, students must also learn about the other types of errors that can occur in programs, syntax, and runtime. There are 4 standard algorithms that students are expected to learn about. 2 different sorts, the bubble and merge, and 2 different searches, linear and binary search. As well as knowing how they work, they should be able to hand trace their operation on a given set of data and weigh up the pros of a brute force versus a divide and conquer approach. They are expected to be able to evaluate the fitness for purpose of algorithms and judge their efficiency. The final section in this topic covers truth tables. Students are expected to be able to interpret and construct truth tables with up to 3 inputs, taking account of order of precedence rules. Topic 2 on page 9 of the specification focuses on how different types of data are represented in binary. The first section is called binary. Students are expected to understand how patterns of zeros and ones are used to represent different types of data. They will need to learn how to manipulate binary patterns representing signed and unsigned integers, convert them between denary and binary, and between binary and hexadecimal. They must be able to add together 2 binary numbers and perform logical and arithmetic binary shifts. They must be familiar with the concept of overflow and recognize the consequences that overflow can have on program outcomes. Section 2 covers how types of data, characters, bitmap images, and sound are represented in binary, using established encoding standards. Students need to know that the number of available bits determines how many different items can be uniquely represented and the accuracy of a digital representation. Section 3 deals with data storage and compression. It specifies that binary multiples, kibibytes and mebibytes, etc., must be used to express file sizes and data capacity. Students need to know how to construct expressions to convert between units of measurement and to calculate file sizes and data capacity requirements. The need for data compression and lossy and lossless methods of compression are also covered in this section. Topic 3 on page 10 of the specification is concerned with the role of hardware and software components in a computer system. The stored program concept is the focus of section 1. Students need to have an understanding of von Neumann architecture and the role of key components in fetching instructions from memory one at a time, so they can be decoded and executed by the CPU. They need to understand the need for secondary storage to provide long-term retention of programs and data, and how data is stored on magnetic, optical, and solid-state media. Students need to grasp the difference between a general-purpose computer and an embedded system that performs a single specialized function. They should be aware that embedded systems are ubiquitous, with millions of them capable of communicating via the internet. Section 2 focuses on system software that is deployed on the hardware. Students need to know why most computers have an operating system and understand the 4 key roles carried out by an operating system, namely file, process, peripheral, and user management. The spec specifies 5 types of utility software tools that students need to be familiar with. It also requires them to recognize the importance of developing robust software and understand how audit trails and code reviews help to achieve this. Section 3 focuses on language translators, how compilers and interpreters translate human-readable code into machine code that a computer can process. Topic 4, on page 11 of the specification, is concerned with networks. Students must understand why and how computers are connected in networks, including the internet. They're expected to know that data is split into packets for transmission across a network and understand the role of IP addressing and routers in directing traffic on the internet. They need to recognize the need for protocols and know what each layer of the TCP/IP stack does. They should use base 10 units, kilobits, megabits per second to specify data transfer rates and be able to construct expressions involving file size, transmission speed, and time. Section 2 deals with network security, common network security threats and prevention methods used to thwart them. Topic 5 on page 12 of the specification considers the impact of digital technology and some of the issues associated with its use. The first section focuses on environmental issues associated with the manufacture, use, and disposal of digital devices, including the effect of the short-term replacement cycle of smartphones and other personal digital devices. Section 2 considers some of the ethical and legal issues associated with collection and use of personal data, and the use of AI, machine learning, and robotics. Students also have to learn about intellectual property rights protection for computer systems and software. Section 3 deals with threats of digital systems and data and how to guard against malware and other security risks. Ofqual stipulates that all GCSE computer science specifications must assess students' ability to apply computing-related mathematics. This slide outlines how this requirement is addressed in this specification. Students are using computing-related maths, perhaps without even realizing it, when they convert between binary, denary, and hex, when they add together binary numbers, perform binary shifts, use arithmetic and relational operators in expressions, write code that performs a calculation, use logical operators in truth tables, etc., etc. Topics 1 to 5 are assessed in paper 1. So before looking at topic 6, we'll take a brief look at paper 1. Paper 1 is a conventional written exam paper. It's set and marked by Pearson, marked out of 75, and contributes 50% to a student's final grade. Questions are presented in an answer booklet with spaces for students to write their answers using a black pen. There are 5 compulsory questions, each targeting one of the 5 topics. The order of the topics in the paper will change from one series to the next, so as to avoid creating the impression that some topics are easier or more demanding than others. Questions will ramp up in difficulty. The majority of marks in each question, the majority of marks in early questions target low and medium grades, whereas in later questions, most marks target medium and high grades. Each question consists of multiple parts. Students should attempt to respond to all question parts. Even if their answer is incomplete, they may be able to pick up some marks. Paper 1 has 2 high tariff questions. One requires an extended written response, an essay, and the other requires some form of diagram or drawing. This slide provides a breakdown of the question types used in paper 1. There's a good mix of question types. Each question starts with a command word. They're listed here in the second column. We've significantly reduced the number of command words that can be used and clarified the nature of the response required for each. The command word taxonomy is in Appendix 1 on pages 27 and 28 of the specification. Roughly 30% of the marks in paper 1 are allocated to questions that require straightforward knowledge recall, such as multiple choice and short open response questions. Multiple choice questions use the command word identify and are worth 1 mark. There are 4 answers to choose from. Students put a cross in the box next to the answer they think is correct. If they change their mind, they put a line through the box and then mark their new answer with a cross. Short open response questions use the command words give, name, state, and define, and are worth 1 or 2 marks. They generally require recall of 1 or more facts about the subject content. Medium open response questions use the command words describe and explain. They have a higher mark tariff of 2 to 4 marks and require students to produce a more substantial written response. There is 1 6-mark extended response question that uses the command word discuss. Students have to produce an essay-style structured response. There's also 1 high-tariff non-written 6-mark question that may require students to produce an algorithm, draw or complete a diagram, or fill in a trace table. Paper 1 will have similar proportions of the question types shown in the table in each assessment series. This will ensure that the question paper students are presented with is familiar without being predictable. Detailed, high-quality mark schemes ensure that marking is reliable and consistent. Marking will be positive and valid responses will be equally rewarded. Clear wording and standard notation make the principal examiner's expectations clear and unambiguous. Marking points are indicated and, where appropriate, an example answer is provided, although this doesn't prevent alternative valid responses from gaining marks. Additional guidance provides extra pointers for examiners on what are acceptable and unacceptable responses. For extended open written responses, such as question 4E in the sample assessment material, there is a levels-based mark scheme consisting of indicative content plus a set of descriptors describing 3 levels of response. Examiners use the principle of best fit to decide the mark for a response. You can find out more about this paper in the Getting Started on Paper 1 Principles of Computer Science pre-recorded event. We've compiled some exam tips for students preparing for Paper 1. 2 items that have been highlighted on principal examiner reports in the past are the need to use subject-specific terminology accurately and to write as legibly as possible. Watch the time to make sure there is the opportunity to respond to every question. Now let's go back to the subject content and look at topic 6. Learning to program is a core component of any course in computer science. Students must be competent at designing, reading, writing, debugging, and refining programs. This topic specifies what skills they must have developed and practiced, and what programming constructs they must be able to use. Their practical capability is assessed in Paper 2 and contributes to 50% of their overall grade, a powerful incentive for them to learn to program. Although split into 2 topics, computational thinking, topic 1, and this topic, are 2 sides of the same coin. Topic 1 provides the theory that underpins the practical work required in topic 6. A strong recommendation is that you can teach them together. Section 1 specifies the programming skills that students should demonstrate when developing code. They learn about the benefits of using decomposition and abstraction in topic 1, Now they're expected to employ these useful techniques to help them read, write, analyze, and refine programs. Similarly, what they learn about types of errors in topic 1 will help them locate and fix bugs in their code. Producing readable code is considered good practice. This is especially so when an examiner needs to see how your code functions in order to award marks to it. Just as they learn to do with algorithms, students should be taught how to evaluate a program's fitness for purpose and efficiency. The remaining sections in this topic detail the programming constructs and components students need to recognize and be able to use. The Programming Language Subset, PLS for short, translates these general terms into actual Python constructs that students must be able to use. Take, for example, repetition and iteration. Students need to be able to write programs that use these components. By repetition, we mean code that keeps executing in a loop while a condition is true. Useful when there's no way of knowing in advance how many times the loop must go around. The PLS specifies that students should use the Python while construct to implement repetition. Iteration is slightly different because instead of using a test to determine whether a loop is repeated, it carries on repeating for the length of the data structure, which could be a count being manipulated. The PLS specifies that students should use the Python for-in construct to implement iteration. Similarly, the specification lists the primitive and structured data types that students need to know about using generic terms, rather than Python-specific ones. The PLS converts these into Python speak, i.e. integer is equal to int, real equals float, etc. Students are expected to know the difference between an array and a record structure, even though in Python, both are created using a list. If the data type is the same for all the elements in a list, then students should think of it conceptually as an array. If the list holds elements with a mixture of data types, it should be thought of conceptually as a record. Similarly, although Python doesn't have constants, students ought to know what a constant is, distinguish constants from variables in their programs by using uppercase characters to name them, and adhere to the convention of not changing the value of a constant once it has been assigned. Why use generic terms rather than Python-specific commands? We were very clear from the outset that the qualification must be a GCSE in Computer Science, not in Python. We want students to learn general principles and concepts so as to make it easy for them to apply their knowledge in different contexts using different programming language at a later stage in their learning journey. Section 4 covers input and output, including file handling, validation, and authentication. In some instances, questions in the exam may require candidates to read in data from a file. Where this is the case, a comma-separated value text file will be provided, along with the code snippets they will use. Similarly, a question may require candidates to write to or amend data in a file, in which case the data file must be submitted for marking along with the candidate's programming file, along with the candidate's program files. Section 5 lists the arithmetic, relational, and logic operators students will need to use in their code. The symbols Python uses to represent these are listed in the PLS. The final section in topic 6 deals with subprograms. Students will have learned the benefits of using subprograms in topic 1. Here, they're expected to use them. The PLS lists the built-in and imported functions that the students should know about and how to use. These include some from the Turtle Graphics library module. As well as using ready-made ones, students must be able to write subprograms themselves. Python doesn't differentiate between functions and procedures. They're both referred to as functions, but the PLS makes a conceptual difference between the two, which students will need to understand, again, in the interest of supporting progression. Python is an object-oriented language. You can create classes, objects with attributes and methods, all of which is way beyond what we expect students in Key Stage 4 to do, which is one of the reasons why we felt it necessary to specify a subset of the language, the PLS, which students are required to learn in order to access the assessment. The PLS is a reduced set of Python 3 programming constructs. The constructs contained in it are found in most high-level programming languages and form a good foundation for progression. All the questions set in paper 2 can be solved using only the functionalities presented in the PLS. This means that more class time can be used for teaching computational thinking and problem solving rather than all the syntax and libraries provided by Python. While there is nothing to prevent students learning more complex constructs or approaches, not including the PLS, there's no need for them to do so. However, should they use a valid technique outside the scope of the PLS to answer an exam question, they will of course be credited with the mark. The PLS will be reviewed on an annual basis to ensure that it remains up to date and relevant, and the version in place on the 1st of September will be the PLS that covers the assessment in the subsequent summer series. For pragmatic reasons, and to ensure comparability, Python 3 is the only approved language. Python 2 should not be used. The choice of programming language wasn't taken lightly. There are pros and cons to every language, but our research indicated that the majority of teachers already use Python for GCSE, even those who told us that they would be prepared to swap if it meant their students would take an on-screen practical exam. Python has a lot going for it, not least that it is free and open source, and there are lots of free and paid-for resources and training available. From a purely pragmatic point of view, preparing students, training teachers, and providing support is much more manageable with just one language. One big plus point for opting for just one high-level language is that students no longer have to learn a separate semi-formal pseudocode. We've taken the opportunity to redefine what we mean by pseudocode, an informal written description of a program using imprecise English language statements with no need for any strict programming syntax. Paper 2 is an on-screen exam that assesses topic 6. Students answer questions by manipulating program code on a computer. We think this will give them more practical and engaging assessment experience than they'd get from answering code questions on paper. This is not an online exam. Students don't need and mustn't have access to the internet during the exam. The question paper itself is printed. Like paper 1, it is marked out of 75 and contributes 50% to a student's final grade. There are 6 compulsory questions, all involve working with code. Students must use Python 3, but schools are free to choose which IDE or editor to use. As with paper 1, students should attempt every question. Partial marks are awarded. The paper is scaffolded. Questions become progressively more challenging, with the final question requiring candidates to write a program from scratch. Each question has a suggested time. This is for guidance only. Our paper 2 uses 3 levels-based mark schemes for the higher level questions at the later stages of the paper. These questions will also have a component of point-based marks. The level-based mark scheme grids are functionality, design, and good programming practices. Candidates get a mark for each accurate piece of code in their response. These are the points-based marks, and a holistic mark awarded for the quality of the overall response from the levels-based mark scheme. Examiners use one or more of the levels-based mark schemes to determine the latter. We'll talk more about this in the Getting Started on Paper 2, Application of Computational Thinking pre-recorded event. Paper 2 uses just two command words, amend and write. Amend requires candidates to make changes to a piece of code. For example, by amending a program so that it performs differently in order to correct an error. It also includes adding to code, deleting from code, or arranging lines of existing code. Write requires candidates to create program code. While not strictly speaking command words, open and save also direct students to do something, i.e. open the named file in their IDE of choice, save their work in their secure exam profile user area. A range of question types are used. Questions in the early part of the paper will require candidates to follow instructions to write lines of code and fix errors. Questions further on in the paper are likely to involve converting a given algorithm into code, putting lines of code in the right order, and improving readability. Towards the end of the paper, questions will be more open. For example, question 5 in the sample assessment materials requires students to write a program that calculates values using a formula based on a given input. To achieve the marks for this question, students need to analyze the problem to identify its component parts, and then design, write, and test the program to ensure it meets the requirements and solve the problem. This slide gives some top tips for students to help them tackle paper 2. Knowing how to use their IDE properly, especially its debugging tools, will save them some time. Having a backup copy of the original files means that if the version they are working on gets significantly changed, they can always start over with a clean slate using the original if they need to. Save work regularly, just in case a technical fault occurs. Some questions are quite long because they have to describe exactly what is required. Requirements are bulleted to make it easier for candidates to tick them off. Good old-fashioned advice that applies to all exams: if they get stuck on a question, they should move on to the next one. They can always go back if they have time at the end. Be sure to run the code to make sure it actually functions properly. If part of your code doesn't work or run, then comment it out. This way, the remainder will actually run. There'll be more about this in the session on paper 2 later in this series. There's detailed information about managing the practical exam in the Instructions for the Conduct of the Examination, ICE, document, available in your download pack. Candidates answer paper 2 on a computer using a locked-down exam profile. Before the exam takes place, centres must set up a designated secure user area for each candidate. On the day of the exam, candidates must download, unzip, and place the secure files in each candidate's secure user area. Candidates must save their programming code responses in a designated folder in their secure area. They must not be able to save any files that they produce during the exam anywhere else, and must not be able to access this area at any time other than during the exam. There is no need for candidates to have access to a printer during the exam, nor should they be provided with printed copies of the secure data files. Candidates are not allowed to refer to textbooks, centre-prepared manuals, or access shared folders during the examination, but may use the offline help facilities provided by the IDE. At the end of the exam, centres must create a zipped folder for each candidate containing all files that they created during the exam and upload them to Pearson to be marked. A new version of the ICE document with more detailed information will be made available nearer to the first exam session in summer 2022. That concludes the first session of this Getting Ready to Teach event, and you can now move on to session 2.